Okay, so in this video we want to begin our study of continuous probability. So technically continuous random variables are no longer on the course, but again, like I did for discrete random variables, I think it's important to talk through the theory of what's happening with continuous random variables before we then look specifically at the normal distribution, which is an example of a continuous random variable. So I think it's important that we get some of these ideas straight before we move on to that. So once again, like the discrete random variables video, I'm not going to expect that you complete the exercise work from this section, but I do want you to watch through the theory and to work through the examples with me. Okay, so a continuous random variable is one that can take any value in an interval of the real number line. So there's no limit to the level of accuracy to which a continuous random variable can be measured. So this is the difference between discrete data versus continuous data. Okay, so discrete data, the data can only take particular values. Usually whole number values would be most common, but that's not always the case. Whereas continuous data can be measured to any level of accuracy. Okay, in fact, the only restriction is the accuracy of your measuring instrument. Okay. Generally speaking, one of the easiest ways to distinguish between discrete and continuous is discrete variables can often be described as a number of something. Number of times I roll a 6, number of people with blue eyes, number of red cars that drive past as I'm watching the road for 2 hours, or whatever it might be. Okay? Whereas continuous random variables are usually measurable quantities. So height, weight, time, length, distance, whatever it might be. Okay, so quantities that we would measure versus quantities that we would count is one of the easiest ways to make the distinction. I'm sure someone can come up with examples that don't fit that category, but for all intents and purposes, that's going to work for you. Okay, so as I said, when we have continuous random variables, it's usually something that's measurable, and the level of accuracy to which we can measure that thing is only really restricted by our measuring instrument. So let's say, for example, we're measuring a person's weight in kilograms. We're only restricted by the scales that we're using. Okay, so if we measure a person's weight as, say, 70 kilograms, it could actually be 69.8 kilograms or 70.1 kilograms, but it's just that my set of scales only measure to the nearest kilogram. Okay. If I've got better scales and they measure to 1 decimal place, then I might be able to actually weigh them and say, okay, this person actually weighs 69.8 kilograms. But again, I'm still being limited by the fact that my scales only show me 1 decimal place. Their weight might actually be 69.82 kilograms or 69.79 kilograms. Okay, we can't possibly know that. We could go on forever. Even if I can give the weight to 10 decimal places, I'm still being restricted. I'm still limited by the measuring instrument, and if I were to actually, be able to round to more decimal places, I might be able to narrow it down more precisely. So one of the key things with continuous probability is it's not ever possible to measure a value exactly. Okay, and so because we can't actually measure the weight exactly, the probability of a person weighing exactly something is 0. Okay, so for this reason, continuous variables always need to be grouped. So let's say we measure the weights of a large group of randomly selected people, and we construct a histogram to show that. Okay, and so we've got this histogram here showing the weights. Obviously, I haven't got a full scale in here, but what we can see here is if we've got this histogram, the probability that someone weighs between 82.5 and 83.5, which is the scale for this particular bar in the histogram, could be found by dividing the shaded area on the histogram by the total area of the histogram. Okay, so that would make sense. If I want to work out what's the probability someone's in this group, if I did this area divided by the total area of the histogram, then I would have the probability of someone being in that group. Because the area essentially corresponds to the height, basically, because this width is 1, so the area is going to be 1 times whatever that height is. Okay, so, and that height is the frequency, so how many people fit in that category if we've got a histogram. So this would be the number of people in that category over the total number of people, which we could find by adding up all the total areas of all the bars in the histogram. Okay, so if we were then to scale the histogram, so instead of this being the number of people in that category, it was the proportion of people in that category. And so therefore that would mean that the total area of the histogram would be 1. And so then we wouldn't actually need to divide by total area because total area is just 1. And so then the probability that someone weighs between 82.5 and 83.5 kilograms would just be that shaded area here if the total area of the histogram was 1. Alright, so then if we were to increase the sample size so that we can decrease the width of the class intervals, the bars are going to get narrower and narrower and narrower. So instead of having a bar that represents 82.5 to 83.5, if we've got lots and lots of data, we can actually have a bar that measures 82.5 to 82.6, and we'd have enough people that would fit in each of those very small narrow categories to still create a histogram. And if we kept doing that, this idea that if we make the intervals narrower and narrower, we're essentially going to be able to create a smooth curve that defines the probability distribution. Okay, so the more people, the more data, the narrower we can make the bars in the histogram until we make them so narrow that essentially we're modelling what's happening with a smooth curve. This curve, so the red curve drawn here, is called a probability density function, and it's used to describe the probability distribution of any continuous random variable. And so now, if the probability distribution is represented by that smooth curve, that smooth red curve here, okay, and again, remember we've scaled it to be 1, so the total area under this smooth red curve is 1, then the probability that someone weighs between this and this would be this bit of area under the curve, given that the total area is 1. And so we find that calculating an integral, so an area under a probability density function, gives us a probability. Alright, so this is at the core of what we're doing when we have continuous random variables. So in general, for a continuous random variable, x, with a probability density function f, the probability that x is between a and b would be found by finding the integral of f of x, which is the probability density function, between a and b. And again, it relies on two facts about the probability density function. The first one is the probability density function has to be bigger than or equal to 0 for all x. So it can't go under the x-axis because this would be implying negative probabilities. Okay, so it has to be bigger than 0. And the total area under the probability has to be 1. Under the probability density function has to be 1. So total area under here has to be 1, so that then we can use an integral to find the probability, because it would be that area divided by the total area, but if the total area is 1, then we don't need to bother dividing by anything. The other thing to note is because for a continuous random variable, the probability that x equals a particular value is 0, it means we can sort of be a bit less precise, although we should accurately interpret worded questions. All these things say the same, okay? Probability that x is between a and b is the same as the probability that x is between a and b inclusive. It's the same as the probability of us including one of the ends but not the other one, okay? And that's because the probability that x equals a is 0. So if we include it or don't include it, it's still the same probability, okay? And I know that idea of the probability of x being equal to something being 0 is not particularly intuitive. But again, it comes back to that. It's actually impossible to measure something precisely. It's sort of that idea. Okay, so let's have a quick look at an example of the sorts of things that we would see in a continuous random variables exercise. So consider f of x as a hybrid function, 12x squared times 1 minus x, where x is between 0 and 1. Sketch the graph of y equals f of x and show that f is a probability density function. Okay, so this is a cubic, okay? It's got x-intercepts when x equals 0 and when x equals 1, okay? It's going to have a turning point at 0 and a cut through the x-axis at 1. And we only want to draw it from 0 to 1. So the cubic essentially would look like this. It's a negative cubic, sorry, negative x cubed. So it's going to do that, okay? That'll be 1, this will be 0. So we only want the bit between 1 and 0, so just the bit that's above the x-axis, which is good because that then makes it a probability density function. Okay, so I'm just going to draw my axes. I'm actually going to draw my graph in a different colour because I want to make a point. So we're going to have a cubic shape. Okay, so that's going to be the point 1, 0. That's obviously 0, 0. And then when you're drawing a probability density function, which you won't really need to do in 2020, but one of the key things that you need to make sure that you do is you actually also draw that part of the function. Sorry, let's try that again. Okay, so both branches of the function, the cubic part and the other part. I don't really need the turning point, although it should probably specify that you don't need to draw it, but it's not relevant to the fact that it's a probability density function. Okay, so sketch the graph, done, and show that f is a probability density function. Okay, so the first thing that's clear is that it can be seen from the graph that f of x is bigger than or equal to 0 for all x. Okay, so that's the first condition for a probability density function. And the second condition is that the total area has to be 1. So we want to show that the integral from 0 to 1, sorry, I'm missing a bracket there, the integral from 0 to 1 of the cubic, because that's the only bit where there's any area, so of 12x squared times 1 minus x, has to be equal to 1. So we want to show that though. We don't assume that. Oops, sorry. We don't assume that and then calculate and end up with some arbitrary meaningless statement at the end that says that 1 equals 1. We just calculate this integral and then hope that we get 1 and then draw a conclusion from it when we do get 1. Okay, so integral from 0 to 1, I might take that 12 out. Up to you though, you probably don't have to. Expanding out that bracket is going to give me x squared minus x cubed. In fact, the 12 is going to be nice with those fractions when I get when I integrate. Sorry, I'm going to leave it. 12x squared minus 12x cubed when we expand. Okay, antiderivative of 12x squared, add 1 to the power and divide by the power, which is why I've left the 12 in. I'm not going to get fractions because 12 divided by 3 is 4. Add 1 to the power is 4, divide by 4, so we get 3x to the power of 4. And we want that between 0 and 1. So that's going to be 4 minus 3, take away 0 minus 0, and so it is 1. Which means, which means that the total area is 1. So that's the other condition for it being a probability density function. Okay, part B, shade the region which represents the probability that x is less than 5. So now that this is a probability density function, the total area is 1. The probability that x is equal to, 0.5, is going to be the area under the curve where x is less than 0.5. So this bit of area here will be equal to the probability that x is less than 0.5. And then part C, we want to find that area. Okay, so we want to find the probability that x is less than 0.5, which means we need to integrate from 0 to 0.5. I'm going to write that as a half just so I can do the algebra a bit more easily. And our PDF was 12x squared minus 12x cubed when we expanded that. So we use PDF for probability density function. We've actually seen that phrase before when we've used the CAS to find binomial probabilities, binomial PDF. Okay, so we want to find this integral. We've already done the antiderivative. We know that it gives us 4x cubed minus 3x to the power of 4. We're doing that between 0 and 1/2. And so that means we've got 4 times 1/2 cubed minus 3 times 1/2 to the power of 4. Take away, that'll be 0 minus 0. Okay, so 1/2 cubed is 1/8, so it's 4 times 1/8. 1/2 to the power of 4 will be 1/16. Okay, so 4 times an eighth is obviously half, but I want to combine that together with the other fraction anyway, so I'm going to leave it as 4/8 because I'm going to need a common denominator, which will be 16ths. So that's 8/16 minus 3/16, and so it is 5/16, the probability that x is less than 0.5. That area is 5/16 of the total area under the curve. Okay, so in most cases, probability density functions have restricted domains or are hybrid functions like what we just saw there. So we rarely technically have to calculate an integral from negative infinity to infinity, but there are some situations where this is required. And we can actually find an integral from negative infinity to infinity by taking a limit. Okay, so since it's not possible to actually sub infinity in to something, we instead look at integrating from negative k to k and taking the limit as k approaches infinity would be how we would do that mathematically. If, however, you've got access to CAS, your CAS does understand this, but technically it's not really. So if you wanted to evaluate an integral to infinity, you can just put infinity in the limit, in the terminal of the integral, but technically if we're doing it by hand, we need to set it up as a problem involving limits. Okay, so let's have a look at this probability density function. Here we've got 2e to the negative 2x where x is bigger than, where x is bigger than 0, and 0 when x is less than or equal to 0. Okay, so 2e to the negative 2x, the negative here reflects that in the y-axis, dilation by 2 from the x-axis and dilation by half from the x-axis, so that's not going to really change much. But the reflection, the fact that it's an exponential going this way, we can work out that y-intercept. So when x equals 0, you'll have 2 times e to the 0, so that's 2 times 1, so it'll be 0, 2. Okay, and we're not going to have this bit, it's only going to be when x is, and that'll be hollow, when x is bigger than 0. And then it's going to be 0 everywhere else. Okay, so we can draw in that graph. Again, I might use a different colour so I can see my 0. So the y-intercept not included is going to be at 2. So as you can see, whilst this topic isn't on the course anymore, it still brings up having to sketch graphs, calculate integrals, so it's all good revision still. And then it's 0 when x is less than or equal to, so including 0, 0, less than or equal to 0. Okay, so there is our graph. Show that f is a probability density function. Okay, so point number 1, it can be seen from the graph that f of x is bigger than or equal to 0 for all x. So that's the first condition. And the second thing is we want to show that the total area under here is 1. Now it's technically an infinite area, but so that's why we need to set it up as a limit. Okay, so we're looking at the limiting value of the area, as the limiting value of the integral, which will give us the area. Okay, so the area is going to be the integral from 0 to infinity. Okay, but we don't write infinity in there, so technically we're going to do the limit as k approaches infinity. It doesn't have to be k, you can use any letter you want, from 0 to k of, was it 2e to the negative 2x? Yep. dx. Okay, so we calculate, we have to keep writing the limit until we actually take the limit. So limit as k approaches infinity. Antiderivative of 2e to the negative 2x, so we can divide by negative 2, which gives us negative 1, e to the negative 2x from 0 to k. And then we're going to substitute, so we still haven't taken the limit, we're still evaluating our integral. And so it's going to be negative e to the negative 2k minus minus, so plus e to the 0. Okay, so let's just go another step before we do our limit. Okay, so that's the same as negative 1 on e to the 2k, and that's plus 1. Okay, so now we can take the limit. So we're thinking about, alright, as k approaches infinity, this power gets really, really big, this gets really, really big, and then when we're dividing 1 by a really, really big number, that's going to limit to 0. Okay, and so we're going to get 0 plus 1, and so it is 1. Total area is 1. So the total area under the PDF is 1. So therefore it's a PDF, probability density function. Okay, find the probability that x is bigger than 1. Okay, so the probability that x is bigger than 1 is going to be, if we look at our graph, so x is bigger than 1, let's say this is 1 here, we're going to be looking at that area there. But thinking about probabilities, actually the easier way to do it that would avoid us having to integrate to infinity would be to find that red area by doing 1 minus the green area, now that we know that the total area is 1. So you can usually set up the integrals to avoid having to integrate to infinity. Okay, so technically it would be the limit as k approaches infinity of the integral from 1 to k of 2e to the negative 2x. But the easier way to do that would be to do 1 minus the integral from 0 to 1 of 2e to the negative 2x. Okay, so that will be negative e to the negative 2x from 0 to 1. So that's negative e to the negative 2 minus minus, so plus e to the 0. Okay, so it's going to be 1 minus minus e to the negative 2, so that's plus e to the negative 2, and then minus e to the 0, which is 1, so minus 1. So 1 minus 1, they're cancelling out, and it's just e to the negative 2. Or we could write that as 1 on e squared. Same thing. Okay, find the probability that x is less than 2 given that x is bigger than 1. Correct to 4 decimal places, so I can use my CAS to evaluate the relevant integrals. Okay, so conditional probability still works here. It works the same all through discrete and continuous variables. So understanding that we need the intersection where x is both less than 2 and bigger than 1 over the second thing. So if x has to be both less than 2 and bigger than 1, that means that x has to be between 1 and 2 over the probability that x is bigger than 1. Okay, we've already worked out x is bigger than 1 in the previous question. Okay, so it's going to be over e to the negative 2. So we just need to work out the probability that x is between 1 and 2. Okay, so that's going to be the integral from 1 to 2 of 2e to the negative 2x. Alright, so if we work that out, shift plus 1 to 2, 1 to 2 of 2 times e, make sure you use the proper e to the negative 2x dx. Okay, so it's going to be e squared minus 1 times e to the negative 4 over e to the negative 2. You could subtract powers if you want there, negative 4 minus negative 2. So it's actually just going to be e squared minus 1 e to the negative 2. But we don't really need to worry about the exact values because we do just want a decimal to 4 decimal places. So we could have just straight away gone to the decimal up here. So 6.3, what did it say? Oh, hang on, we've got a probability that's 6. What have I done? Have I got my function right? 2e to the negative 2x, is that function? Yes. Okay, what have I done? We want to do x less than 2 given x bigger than 1. So integral between 1 and 2. Let me just check that I've typed it incorrectly up here. Integrating between 1 and 2, 2 times e to the negative 2x. Let's just check while we're here that we got our answer to part C correct. So integral from 1, so I'll show you that you can actually make the limit infinity. So if I do integral from 1 to infinity here, yep, so we've got our answer there, right? Okay, so what have I done? So we want to do, let me just do it as the integrals then. We want that integral divided by that integral. Sorry, I think let me just check that it's the same. Yeah, I think I just typed it in the CAS wrong when I did the division, sorry. Okay, so hopefully you were screaming at me telling me what I'd done wrong. So that is actually equal to 0.86, we wanted 4 decimal places, 47. Okay. Alright, measures of centre for a continuous random variable, so mean and expected value, or mean or expected value, sorry, they're the same thing. So for a continuous random variable, it's the same logic as it is for a discrete random variable. We want to do the x value multiplied by its probability and then add all of those up. And so that's essentially what we're still doing here. The x value multiplied by the probability, which is defined by that probability density function, and then in the context of a continuous random variable, adding them all up is the same as integrating over the total domain of the function. So we do the integral over the total domain of the function, which might be from negative infinity to infinity, but more likely it'll have a restricted domain, of x times the probability density function. It's also possible to work out the expected value of a function of x by doing that function of x times f of x. Now that's not really going to come up here. The main reason that's going to come up and the reason I include that here is because we're still going to need to calculate expected value of x squared, which would mean doing the integral of x squared times the probability density function over the total domain, which might be restricted, and if not, from negative infinity to infinity. So you'll remember we need e of x squared in order to find variance, and we're still going to need that here. Okay, so otherwise I wouldn't really worry this year about g of x. expected value of a function. However, also those same properties of expected value still apply with the continuous random variable. If it is expected value of a linear function, you can simply just sort of expand it out. So it's just a times the expected value of x plus b. Okay, if x is the random variable with probability density function f, find the expected value of x. Okay, so in this case, expected value of x is going to be the integral from 0 to 3 of x times the probability density function. Okay, so that is integral from 0 to 3 of 1/3 x squared, which is 1/9 x cubed from 0 to 3, which is 3 cubed is 27 on 9 minus 0. And so the expected value is 3. So remember, expected value is not a probability. That's out of the x value. So the x values here range from 0 to 3. So it has to be a number somewhere within that range. And it actually happens to be 3, the expected value here. Okay, so then we want the expected value of 4x minus 2. So expected value of 4x minus 2. So that's expected value of a linear function. So that's the same as 4 times the expected value of x, take away 2. So 4 times 3 minus 2, 12 minus 2, so 10. And the expected value of x squared, which we're going to need as part of variance, which is why we still include that, is going to be x squared times the function. So that is integral from 0 to 3, of 1/3 x cubed. And so anti-differentiating that, add 1 and add 1 to the power gives us 4, divide by that means we'll have 1/12 x to the power of 4 from 0 to 3, which means we're going to have 3 to the power of 4, which is 81 on 12 minus 0 on 12. So it's just going to be 81 on 12. Again, it's not a probability, so it can be bigger than 1. There's no issue with that. Okay, this in itself is really meaningless. We're going to just need to do that in order to find variance, which we'll talk about in a minute. Okay, percentiles and the median. So other measure of spread is the median, but we might also talk more generally about percentiles because the same logic applies. So a percentile is a value below which that percentage of the distribution occurs. So if we say that we're at the 80th percentile, that means 80% are lower than me and 20% are higher than me. So if I'm at the 80th percentile for height, which I'm certainly not, but if I'm at the 80th percentile for height, that means that 80% of people in whatever the group is that we're talking about are shorter than me, 20% are taller than me. Okay, so the 10th percentile would mean 10th percentile for weight, I don't know, also not true. 10% of people are lighter than me, 90% of people are heavier than me. Okay, so think of that understanding. So essentially when we're told the percentile value, we're sort of being given the probability. So if P is the 10th percentile, that's because 10% of the distribution is below here. So that means the area, the integral from 0 or from the smallest possible value in the domain up to P is going to be 10%. Okay, so integral from negative infinity, or it'd be a number if there's a restricted domain, up to an unknown P, the percentile, is going to equal 10. And that will then, solving that for P, will tell me what the percentile is. Okay. So generally speaking, if the integral from negative infinity to P of f of x is equal to q%, that means that P is the qth percentile of the probability distribution. So for example, if we're integrating from negative infinity up to 4, our probability density function, and we get 0.2, that tells us that 4 is the 20th percentile, okay? Because whatever that probability density function looks like, okay, if that's 4, we've got 20% happening there, okay? So 4 is the 20th percentile. If you have a weight of 4, meaningless, you are at the 20th percentile in this particular distribution. So we know then that median is the 50th percentile. So the median follows the same logic. Finding the median is the same logic. If I integrate from the smallest value of in my domain, which might have to be from negative infinity, but will probably be from a number, up to m, and I get 0.5, that means that m has to be the median. Okay, it's the 50th percentile. Okay, let x be a continuous random variable with the probability density function given by this. Find correct two decimal places, so we'll use our CAS here. That's a trigger for us. It's also just going to make it a bit more efficient, but let's just set up what we need to do to find the median value of x. Okay, so we know that the median, so if we solve the integral from, now we don't need to integrate from negative infinity because the domain practically only starts at 0 because there's no function outside of there. So integrating from 0 up to the median value, integrating our probability density function should give us 0.5. Okay, so we want to know what is m so that we get to the 50th percentile. Okay, so I'm going to solve, shift plus, integrating from 0 up to m. The function is 3/4 times x squared times 2 minus x. Oops, sorry, I don't know why there's a g there. Times 2 minus x, differentiating that with respect to x, and we want that whole thing to be equal to 0.5. If I write 1/2, I'll get an exact value, although it does tell me I can give my answer to two decimal places here. So enter gives me, oh, sorry, I'm not solving for x. My apologies. Let me just undo that. Okay, we're not solving for x, so let's copy that down again. We're solving for m. Okay, so m is going to be approximately equal to two decimal places. So now the other thing is we've got two values here, but we know the median is going to have to be within the domain of the function. So it has to be between 0 and 2. So therefore it has to be 1.2, now to two decimal places, that would be 1.23. So that is since the median has to be within the domain of the probability density function. We then want to find the 70th percentile of x. So this would be integrating from 0 up to an unknown percentile value, up to an unknown value I should say, the function, and we this time want that to equal 0.7. So editing the same thing, in my case I won't bother to change the letters. We want the answer to two decimal places, so I'll just type 0.7. If I did want the option of an exact answer, I'd type 7/10, so I've got a nice exact equation, and therefore my CAS can give me an exact value if it's possible. Again, it has to be between 0 and 2, and so p has to be approximately 1.46. Again, since p has to be between 0 and 2. So because I've ignored a solution, I'm going to be clear about why I ignored a solution. We would expect p to be bigger than m. Okay, the 70th percentile should be a higher value than the 50th percentile, so it makes sense that p is 1.46, which is larger than the median of 1.23. Okay, so measures of spread, we still have variance and standard deviation. So formulas for variance are still the same. It is the average of the squared distances from the mean, which means in terms of calculation formula, expected value of x squared minus the expected value of x all squared. And then the standard deviation is the square root of the variance. We tend to use, I've introduced this notation before, and same for the mean or expected value, we tend to use mu for the mean and sigma squared for the variance, which means sigma is the standard deviation. Okay, we tend to use the Greek letters when we're talking about continuous random variables, and e of x and var x and sdx when we're talking about discrete, a little bit more, but both are perfectly interchangeable between the two. Other measures of spread would be the range and the interquartile range. So the range is simply the difference between the smallest and largest possible values. So maximum value minus minimum value. So we're going to see that just by looking at the domain. What's the biggest possible value of x we can get minus the smallest possible value of x we can get. So if we think about this previous example here, the maximum possible value of x is 2 and the minimum possible value of x is 0, so that range would be 2 minus 0. Interquartile range, we want to calculate some percentiles. So interquartile range is the difference between the first quartile, which is the 25th percentile, and the third quartile, which is the 75th percentile. So we would need to work out the first and third quartiles and then subtract them to find the interquartile range. So it gives us the spread of the middle 50% of the distribution. Okay, from the 25th percentile to the 75th percentile, that's the middle 50%, and it tells us, what's the range of those values. Okay, so let's have a look at an example here. Continuous random variable x has a probability density function given by this. First of all, find the value of k. So if there's an unknown value in the probability density function, you're going to have to use the fact that you know that the total area has to be 1. Now I'm going to use my CAS to solve these just because I want to kind of get through this theory and these ideas rather than do the nuts and bolts of the algebra. So in this case we know that the integral of k on x from 1 to 9, which is the total domain of the function, that's going to have to be 1. And so from that we should be able to solve for k. Now it's not a difficult question to do by hand, and it's absolutely the sort of thing you would be able to do by hand in a non-2020 exam, but you're not going to need to do this because continuous random variables aren't on the exam. That isn't to say it isn't still some good integration practice for you to be doing this, and that's where I think this is a bit of a loss out of the course. It was a really nice point in the course that brought quite a lot of work together. So we're solving for k, when we make that derivative equal to 1, and so we find that k equals 1 on 2 times log e of 3. Now, you'd probably have ended up with that looking a bit differently if you did it by hand, to be honest, but that's okay. Okay, so find the mean and variance of x, giving your answers correct to 3 decimal places. Okay, so this means now that our function is, our probability density function is now 1 on 2x times log e of 3. So I'm just literally putting that back in there. Okay, obviously the x you can write after or before. I'm just going to write it that way, where x is between 1 and 9. That's essentially the probability density function we're dealing with. Okay, so find the mean. So expected value of x is the integral from 1 to 9 of x times 1 on 2x log e of 3. Okay, so you notice the x's will actually cancel out there. So it's actually the integral from 1 to 9 of 1 on 2 log e of 3. Okay. So it is shift plus integral from 1 to 9 of k. So I'm just going to get that from up there. Already got that sitting there. I have to lose that k though. Oh, sorry, it has to go in there. So I'm going to type it. That was silly. 1 on 2 times log e of 3, and we want to differentiate that with respect to x, and that is going to be 4 on log e of 3. Sorry, but we want 3 decimal places. Expected value of x is 3.641 to 3 decimal places. We want expected value of x squared because we next want to find the variance, so we need expected value of x squared. So that's integral from 1 to 9 of x squared times 1 on 2x log e of x, which means it's going to be integral from 1 to 9 of x on 2 log e of 3. Sorry, it's not log e of x, it's log e of 3. And so I'm just going to edit this calculation because it's the same thing but with an x up here. So that's going to be 20 on log e of 3, which is approximately 18.205 to 3 decimal places. And so therefore the variance of x, although the rounding here doesn't really matter because that's not an answer, we're only being asked for 2 values, the mean, which is there, and the variance. So however we round, this isn't going to matter, and I'm going to use it exactly in my CAS anyway. So variance of x is expected value of x squared, take away expected value of x all squared, which means it is 18.205 minus 3.641 squared. Okay, nice exact values with your CAS, there's no reason not to. It is that value there minus, so don't use rounded values to then calculate another answer that's got to be rounded, minus that squared, and that to 3 decimal places is 4.948. So those are the 2 answers to the question, the mean and the variance. Find the range and the interquartile range. Okay, so the range is nice and easy. It is the largest possible x value, which is 9, minus the smallest possible x value, which is 1, and so the range is 8. For the interquartile range, we're going to need the 2 quartiles. Okay, so if we integrate from 1 up to the first quartile, Q1, our probability density function, which is 1 on 2x log e of 3, if that equals 0.25, that's going to give us Q1. Okay, and if we integrate from 1 up to Q3, it should equal 0.75 to give us the third quartile. And then the interquartile range is going to be the third quartile minus the first quartile. Okay, so let me do those. So let's see if I can edit this last integral that I just did here. I have to edit a bit because we want 1 on the numerator and there should be an x in the denominator. Wherever you put it, that's fine. We want to integrate, I need to solve. I'm just going to call that p. I just pressed enter because I forgot about the solve. So menu 3.1, we want to solve that integral to p. We need it to be equal to 0.25 and we want to solve for p. Okay, again, now p has to be somewhere between 1 and 0. So this is Q1. Sorry, not between 1 and 0. Between 1 and 9, which is the domain of the function. So it's going to be Q1 is 1.732. Okay. Q3 is going to be solving that same equation, except we want it to equal 0.75 instead for the 75th percentile, which is the third quartile. Has to be between 1 and 9, so Q3 is 5.196, and then we're going to do 5.196 minus 1.732. So again, we can be more accurate than that in our CAS because we do want the final answer to 3 decimal places. So don't use 2 answers rounded to 3 decimal places to then calculate another answer rounded to 3 decimal places. Always work more accurately than that. So I'm just going to type in as much as I can see here on the CAS. 5.196152423. Usually I would copy the answer down, but because it's muddled up in all this, there's 2 p-values, it's actually going to be more complicated than that. So I'm not going to copy, I'm just going to type out what I can see. That's enough accuracy, more than enough accuracy really. If you just went to 4 or 5 decimal places, that should be enough to be sure that you're okay. Okay, so to 3 decimal places, 3.464 is my interquartile range. So range is 8, all the values, all of the x values fit within a span of 8 values, but the middle 50% are in a span of about 3.5 values. Okay, so usually I would set this work from exercise 15A, B and C. It's not work that will be accessible in the exam, so I'm not going to set the work. I just wanted you to have talked through that theory, got an understanding of when we have a continuous random variable, what it is to be a continuous random variable, so usually looking at a measurable quantity rather than a countable quantity. In that instance, we can construct a function that describes, which we call a probability density function, that describes the probabilities. And we understand that the probability is connected to the area under the probability density function. Also understanding that the probability of x being equal to a particular value is 0 when we have a continuous random variable. And also understanding that our ways of calculating mean and variance and standard deviation still extend. Those formulas still apply here. We obviously just need some integrals to calculate the key values. Alright, so in the next video we'll be moving on to the normal distribution, so you can sort of head straight on to that rather than pausing to do some exercise work here.